Russell's paradox and Gödel's response. In 1901, mathematician Bertrand Russell discovered a paradox that threatened to destroy mathematics. He was examining set theory, the foundation of mathematics where everything is built from sets, collections of objects. Russell asked a simple question: can a set contain itself as a member? Some sets contain themselves. The set of all sets is itself a set, so it contains itself. The set of all things that aren't chairs includes itself, because the set itself isn't a chair. Other sets don't contain themselves. The set of all chairs isn't itself a chair, so it doesn't contain itself. Russell then defined R and war, the set of all sets that don't contain themselves. Now ask, does R contain itself? If R contains itself, then by definition it must be a set that doesn't contain itself. Contradiction. If R doesn't contain itself, then by definition it must be in the set of all sets that don't contain themselves, which is R itself, so it does contain itself. Contradiction. Either way leads to contradiction. This paradox threatened the foundations of mathematics because set theory was supposed to be the bedrock on which all mathematics was built. If set theory contained contradictions, then all of mathematics might be inconsistent. Mathematicians worked frantically to resolve this. The solution was to create axiom systems with rules preventing problematic self-referential sets. The Zermelo-Fraenkel axioms reorganized set theory to forbid sets like R from existing. Problem solved. No more Russell's paradox. But this solution created a much bigger problem, revealed by Kurt Gödel in 1931. Gödel proved his incompleteness theorems, showing that any axiomatic system powerful enough to do arithmetic must be either incomplete or inconsistent. You can't have both completeness, proving all true statements, and consistency, never proving false statements. Specifically, Gödel showed that within any consistent mathematical system, there exist true statements that cannot be proven within that system. More devastatingly, no system can prove its own consistency. If a system proves it's consistent, that proof is meaningless because it might come from an inconsistent system. This is far worse than Russell's paradox. Russell found one paradox in one area of mathematics. Gödel proved that paradoxes are unavoidable in all of mathematics. You can't build a perfect mathematical system. Something must be sacrificed. The resolution to Russell's paradox, creating restricted axiomatic systems, directly enabled Gödel's proof. The very act of formalizing mathematics rigorously enough to avoid Russell's paradox created systems formal enough for Gödel to prove they must be incomplete. So, we traded a specific paradox, Russell's set, for a universal limitation, Gödel's theorems. We fixed the contradiction in set theory, but discovered that all mathematical systems contain unprovable truths. We resolved one paradox by accepting that paradoxes are fundamental to mathematics itself. Some mathematicians now argue we should accept that mathematics is fundamentally incomplete and focus on exploring what can be proven rather than hoping for complete systems. But this means accepting that mathematical truth exceeds mathematical proof. There are true statements we can never prove, paradoxes we can never resolve. The larger paradox: we solved Russell's paradox by creating mathematical systems rigorous enough to avoid it, which allowed Gödel to prove that those systems must contain unsolvable problems. The solution created something worse than the problem: the grandfather paradox and many worlds. The grandfather paradox is time travel's most famous logical problem. If you travel back in time and kill your grandfather before he meets your grandmother, then your parent is never born, which means you're never born, which means you can't travel back in time to kill your grandfather, which means he does meet your grandmother, which means you are born, which means you can travel back in time to kill him. Infinite logical loop. This paradox has troubled physicists since Einstein's equations were found to permit closed time-like curves, paths through space-time that loop back to their starting point, allowing time travel. If the equations allow it but logic forbids it, something is wrong. The proposed solution is the many worlds interpretation of quantum mechanics combined with timeline branching. When you travel back in time and kill your grandfather, you create a new timeline branching from that point. In this new timeline, you're never born. But you came from a different timeline where you were born. No paradox. You exist in timeline A, travel to timeline B's past, and prevent your timeline B self from existing. Timeline A remains unchanged. Problem solved? Not remotely. This solution creates problems far worse than the grandfather paradox. First, it requires accepting that every quantum event creates multiple parallel universes, potentially infinite universes splitting every instant. This is an extraordinary ontological commitment. We traded one logical problem for infinite universes. Second, it raises the question, what determines which timeline you arrive in when you time travel? If infinite timelines exist, why do you arrive in one where you can affect events? The probability of arriving in any specific timeline approaches zero if infinite timelines exist. Why don't you arrive in a timeline where different quantum events made your grandfather a different person entirely? Third, it creates the problem of free will across timelines. You make decisions in timeline A based on your timeline A history. You time travel to timeline B where that history doesn't exist. Are you the same person? Your actions are determined by experiences that never happened in the timeline where you're acting. You're essentially an alien from another universe whose motivations make no sense in the context where you're acting. Fourth, and most devastating, if every time you make a choice, the universe splits into versions where you made different choices, then you is meaningless. There are infinite versions of you making every possible choice. The concept of personal identity dissolves. You solved the grandfather paradox by destroying the concept of a single continuous self. Fifth, the measurement problem in quantum mechanics becomes worse. In standard quantum mechanics, measurements collapse superpositions to definite outcomes. In many worlds, nothing collapses. All outcomes occur in different branches. But then, why do we experience one definite outcome? The many worlds interpretation trades the measurement problem for the preferred basis problem. Why do we experience one branch rather than being aware of all branches? Sixth, conservation laws become problematic. When the universe splits, does total energy double? If not, where does the energy for the new timeline come from? If yes, doesn't this violate conservation of energy? Some interpretations say the total energy is conserved across all branches, but this is bizarre. Energy exists in multiple non-interacting universes that somehow share a conservation law. The grandfather paradox is one logical contradiction. The many-world solution creates infinite universes, destroys personal identity, makes probability meaningless, creates measurement problems, threatens conservation laws, and requires accepting that all possible outcomes of every event actually occur. We resolved a time travel paradox by accepting something far more paradoxical, that reality is constantly branching into infinite parallel versions, that you exist in countless forms making every possible choice, and that the universe you experience is one arbitrary branch among infinite others with no explanation for why you're aware of this branch rather than another. The grandfather paradox was a problem for time travel. Many worlds is a problem for reality itself. The liar paradox and Tarski's hierarchy. The liar paradox is ancient. This statement is false. If it's true, then it's false. If it's false, then it's true. Self-referential contradiction. For centuries, philosophers treated this as a curiosity. In 1936, Alfred Tarski resolved it by proving that truth cannot be defined within a language. It requires a meta-language. A sentence in language L can only be evaluated as true or false in meta-language L1, which talks about L. And L1's truth requires meta-meta-language L2, and so on infinitely. This solution eliminates the liar paradox. The sentence, "this statement is false," can't refer to its own truth, because truth requires a higher level language. The statement isn't in the same language as its truth evaluation, so the paradox dissolves. But Tarski's solution creates an infinite hierarchy of languages, each unable to evaluate its own truth. You can never step outside the hierarchy. There's always a higher level needed. This creates several larger paradoxes. First, it makes truth fundamentally undefinable. We can define truth for lower languages from higher languages, but we can never define truth absolutely. There's no final language that can evaluate all truths, including its own. Truth becomes relative to linguistic levels rather than absolute. Second, it creates the paradox of which language we're speaking. When I say snow is white is true, am I in language L or metalanguage L1? If L1, then I can evaluate L statements, but not L1 statements. But my claim about truth is itself an L1 statement, which requires L2 to evaluate. We've created an infinite regress worse than the original paradox. Third, it makes mathematics impossible to complete. Mathematical proofs are statements about mathematical statements. They are inherently metalinguistic. If truth requires moving up the hierarchy, then mathematical truth requires infinite hierarchies. Any mathematical statement's truth requires a higher-level framework, which requires an even higher one, infinitely. Fourth, it destroys the correspondence theory of truth. We intuitively think snow is white is true if snow is actually white. Truth corresponds to reality. But Tarski's hierarchy says truth is a property of relationships between linguistic levels, not correspondence to reality. We traded intuitive truth for infinite abstract hierarchies. Fifth, it creates the paradox of natural language. Humans speak single natural languages like English, not infinite hierarchies of formal languages. Yet, Tarski's solution requires hierarchies. Either natural language is incoherent, it allows liar sentences without the hierarchy to prevent them, or humans are somehow simultaneously operating at all levels of the hierarchy while appearing to speak a single language. Sixth, the hierarchy itself creates Gödel-like limitations. Each level in the hierarchy is a formal system. By Gödel's theorems, each level has unprovable truths, so even with infinite hierarchies, there remain truths that can't be captured. We resolved one paradox by accepting that truth is fundamentally incomplete across infinite dimensions. The liar paradox was one self-referential sentence creating contradiction. Tarski's resolution requires infinite languages, makes truth relative and undefinable, creates infinite regress in every truth claim, destroys intuitive correspondence to reality, makes natural language incoherent, and still leaves unprovable truths. We solved a paradox in one sentence by making all truth paradoxical. Zeno's paradoxes and infinite divisibility. Zeno of Elea created several paradoxes about motion around 450 BCE. The most famous, Achilles races a tortoise. The tortoise gets a head start. Achilles must first reach where the tortoise started, but by then, the tortoise has moved ahead. Achilles must reach that new position, but the tortoise has moved again. This repeats infinitely. Achilles must complete infinite steps to catch the tortoise, which seems impossible. Yet, obviously, Achilles does catch the tortoise. For 2,000 years, this puzzled philosophers. In the 19th century, mathematics resolved it with calculus and infinite series. Yes, Achilles completes infinite steps, but the infinite series converges to a finite sum. Infinite steps don't take infinite time if each step is proportionally shorter, problem solved mathematically. But the philosophical implications create far bigger paradoxes. First, we've accepted that completing infinite tasks is possible. Achilles performs infinite actions in finite time. This seems to violate the concept of infinity. If you can complete infinite things, in what sense are they infinite? We've redefined infinity to mean very large but completable, rather than uncompletable. Second, we've accepted that space and time are infinitely divisible. Between any 2 points, infinite intermediate points exist. Between any 2 moments, infinite intermediate moments exist. This creates the composition problem. If everything is made of infinite parts, how do finite things exist? How do infinite points compose a finite line? Third, this creates the measure problem. If a line contains infinite points and each point has 0 length, how does the line have positive length? Infinite zeros summing to positive values violates arithmetic. Standard mathematics says point sets and lengths are different types of things, but this just labels the paradox rather than resolving it. Fourth, it creates the boundary problem. If space is infinitely divisible, where is the boundary between objects? At any proposed boundary, you can zoom in and find more space that must be divided between the objects. Objects become fundamentally indefinite. There's no fact about where one thing ends and another begins. Fifth, quantum mechanics suggests space might not be infinitely divisible. If there's a smallest length, the Planck length, then infinite divisibility is false. But if space is quantized, Zeno's paradoxes return in a new form. How does discrete space allow continuous motion? Jumping between quantum positions creates the paradox of what happens in between the jumps. Sixth, the resolution created the continuum problem. Mathematical real numbers represent continuous space, but they have bizarre properties. There are more real numbers than counting numbers, yet most reals are indescribable. They can't be defined or computed. The numbers representing space are mostly ineffable. We solved motion paradoxes by accepting that space is described by numbers we can't specify. Seventh, this led to the Banach-Tarski paradox. Using infinite divisibility and the axiom of choice, you can decompose a sphere into pieces and reassemble them into two spheres identical to the original. Accepting infinite divisibility leads to accepting that one thing can become two things of the same size without adding anything. The cure is worse than the disease. Zeno said, motion is paradoxical because it requires completing infinite steps. We said, completing infinite steps is possible because infinity works differently than intuition suggests. But accepting this creates paradoxes about composition, measure, boundaries, the nature of numbers, and ultimately leads to mathematical proofs that one thing can become two. We resolved paradoxes about motion by making space itself fundamentally paradoxical. The Bootstrap paradox and ontological loops. The Bootstrap paradox involves objects or information with no origin. A man travels to the past and gives Shakespeare the complete works of Shakespeare, which Shakespeare then copies and publishes as his own. The works exist, but where did they come from? Not from the man, he got them from Shakespeare. Not from Shakespeare, he copied them from the man. The information has no source. It exists in a causal loop. Physicists exploring time travel initially thought this paradox was resolvable. The solution: consistency constraints. Time travel is possible, but only in ways that don't create contradictions. You can't create information from nothing. You can only create apparent loops that secretly have external sources. But working out consistency constraints creates far worse paradoxes than the Bootstrap problem. First, it requires the Novikov self-consistency principle. Only consistent timelines can exist. But who or what enforces this? If you try to create a paradox, what stops you? The laws of physics would need to conspire to prevent paradoxes, which requires something like fate or determinism at a cosmic level. We resolved one paradox by invoking cosmic scale predetermination. Second, consistency constraints create extreme fine-tuning requirements. For a timeline to be self-consistent through time loops, every quantum fluctuation, every particle trajectory, every decision must align perfectly. The probability of spontaneous consistency approaches zero. Yet, it must happen. This requires something selecting consistent timelines from all possibilities. Essentially, anthropic selection on a cosmic scale. Third, it raises the question, consistent with respect to what? If a timeline loops, its beginning state must match its ending state. But what determines that state? There's no external input. The loop is closed, so the state must be self-determining. Configurations that happen to be consistent with themselves. This is circular. The timeline exists because it's consistent, but consistency means matching itself, which requires it to already exist. Fourth, this creates problems with free will worse than many worlds. If only consistent timelines can exist, and you're in a timeline with time loops, then everything you do was predetermined by consistency constraints. Not just that your actions are determined by prior causes, but that your actions are determined by future effects through temporal loops. You can't choose differently because different choices would create inconsistent timelines, which can't exist. Fifth, quantum mechanics makes consistency constraints incredibly restrictive. Quantum systems explore all possibilities. For a time loop to be consistent, all quantum explorations must sum to a consistent history. The probability that random quantum fluctuations conspire to produce consistency is astronomically small, yet it must happen if time loops exist. Sixth, the resolution suggests that information can exist without creation. If consistency constraints allow closed causal loops, then information in those loops has no external origin. The Shakespeare plays exist because they exist. Pure, ontological loop. We've accepted causeless effects as fundamental to reality. Seventh, this connects to quantum mechanics retrocausality. If future measurements affect past states, as in delayed choice experiments, and consistency constraints select timelines, then the future is determining the past at all times through consistency requirements. Causality becomes bidirectional, with future and past mutually determining each other through consistency rather than flowing forward. The Bootstrap paradox asks, where did the information come from? The consistency constraint resolution says, information can exist in closed loops with no external source, but this requires cosmic fate, extreme fine-tuning, circular self-determination, destruction of free will, quantum conspiracy, and acceptance that causeless causes are fundamental. We resolved one paradox about information origin by accepting that causality itself is paradoxical, circular, retrocausal, and self-determining through consistency constraints we can't explain. Maxwell's demon and information entropy. In 1867, James Clerk Maxwell proposed a thought experiment challenging the second law of thermodynamics. Imagine a tiny demon operating a door between two gas chambers. When fast molecules approach from the left, the demon opens the door, letting them pass right. When slow molecules approach from the right, the demon opens the door, letting them pass left. Eventually, all fast molecules are on one side, all slow molecules on the other. The gas is spontaneously organized into hot and cold sections without energy input, violating the second law, which says entropy must increase. This paradox threatened thermodynamics for decades. The resolution came in the 1960s and 1970s from Rolf Landauer and Charles Bennett. They proved that the demon must store information about which molecules are fast or slow. To reset its memory after each operation, required for continuous function, it must erase information. Landauer showed that erasing information increases entropy, requiring energy dissipation. The entropy increase from memory erasure exceeds the entropy decrease from organizing molecules. The second law is saved. But this solution creates problems far deeper than Maxwell's demon. First, it establishes that information is physical. Information isn't abstract. It has thermodynamic cost. Erasing a bit of information requires energy dissipation. This seems to make information more fundamental than matter or energy. They are manifestations of information states. We resolved a thermodynamics paradox by making information fundamental to physics. Second, it creates the measurement problem in a new form. Any observation requires recording information about the system. Recording information creates entropy. Therefore, all measurements increase entropy. But quantum measurements supposedly collapse superpositions without thermodynamic cost. Or do they? If measurements require information and processing, they must increase entropy, connecting quantum mechanics to thermodynamics in ways we don't understand. Third, it raises the question, is computation physical or abstract? If information has thermodynamic cost, then computation is a physical process bound by physical laws. But mathematical computation is abstract and seems independent of physical implementation. We've collapsed the distinction between abstract and physical, making mathematics energy dependent. Fourth, it creates the problem of consciousness and entropy. If brains process information, and information processing requires energy dissipation, then consciousness increases entropy in the universe. Thinking creates heat. But how much? Can we calculate the entropy cost of a thought? We've made subjective experience thermodynamically quantifiable, but don't know how to quantify it. Fifth, it implies computational limits to the universe. If information is physical and bounded by entropy, there are limits to how much information can exist or be processed in any region of space. The universe has a maximum computational capacity. We resolved Maxwell's demon by accepting that reality is computationally limited. Perhaps even that reality is computation. Sixth, it creates the black hole information paradox. Black holes appear to destroy information by making it inaccessible. If information is physical and can't be destroyed by energy conservation extended to information, then black holes violate fundamental laws. This paradox has occupied theoretical physics for 50 years, with proposed solutions: holographic principle, information encoded in Hawking radiation, creating their own paradoxes about space-time structure. Seventh, Landauer's principle connects information to entropy, but entropy is statistical. It's about macrostates and microstates, not absolute properties. This means information might be observer-dependent. Different observers with different levels of knowledge might measure different information content in the same system, affecting its thermodynamic properties. Information becomes subjective while remaining physical, a paradox about the nature of objective reality. Maxwell's demon was a single-thought experiment threatening thermodynamics. The resolution required making information physical, connecting quantum mechanics to thermodynamics, destroying the abstract physical distinction, making consciousness thermodynamic, imposing computational limits on reality, creating the black hole information paradox, and making thermodynamic properties potentially observer-dependent. We solved one paradox by making information physics' most paradoxical concept. The Banach-Tarski paradox, an axiom of choice. The Banach-Tarski paradox is a mathematical theorem. You can take a solid sphere, decompose it into a finite number of pieces, and reassemble those pieces into two solid spheres identical to the original. One sphere becomes two spheres of the same size, with nothing added. This seems to violate basic conservation. You can't create matter from nothing. The paradox relies on the axiom of choice, which says that given any collection of non-empty sets, you can choose one element from each set. This seems obvious and harmless, but it leads to Banach-Tarski and other bizarre results. Mathematicians initially thought this meant the axiom of choice was false. We should reject it to avoid paradoxes like Banach-Tarski. But rejecting the axiom of choice creates far worse problems. First, without the axiom of choice, many fundamental theorems become unprovable. You can't prove every vector space has a basis. You can't prove Tikhonov's theorem in topology. You can't prove the Hahn-Banach theorem in functional analysis. Much of modern mathematics depends on the axiom of choice. Rejecting it to avoid Banach-Tarski means losing huge portions of mathematics. Second, rejecting the axiom of choice creates bizarre consequences worse than Banach-Tarski. Without it, you can prove there exist sets that can't be well ordered. You can prove there exist infinite sets that can't be compared in size. You can prove the real numbers can be split into more parts than there are real numbers. The mathematics without the axiom of choice is stranger than the mathematics with it. Third, it's been proven that the axiom of choice is independent of the other axioms of set theory, ZF. You can neither prove nor disprove it from the other axioms. This means mathematics has no internal answer to whether the axiom of choice is true. We must choose arbitrarily whether to accept it, making fundamental mathematics rest on arbitrary choices. Fourth, this creates philosophical crisis. Is mathematics discovered or invented? If the axiom of choice can't be proven, and we must choose whether to accept it, are we inventing mathematics by choosing axioms? But mathematics seems to describe objective truths. How can objective truth depend on arbitrary choices? Fifth, accepting the axiom of choice means accepting that decompositions like Banach-Tarski exist mathematically. The pieces of the sphere aren't physically realizable. They're infinitely complex, non-measurable sets. But they exist mathematically. This splits mathematical existence from physical possibility in disturbing ways. Math describes things that couldn't exist physically. Sixth, this relates to the continuum hypothesis, whether there's a set size between countable and continuum. Like the axiom of choice, it's independent of other axioms. You can choose to accept it or reject it. If fundamental questions about infinity are arbitrary choices rather than discoverable truths, mathematical truth becomes conventional. Seventh, physicists use mathematics to describe reality. If mathematics contains arbitrary conventional choices, like the axiom of choice, is our description of reality partially conventional? Do we get to choose which mathematics describes our universe? This makes physical law seem less discovered and more chosen. Eighth, the axiom of choice creates unmeasurable sets, sets that can't be assigned meaningful size or probability. These unmeasurable sets are essential to probability theory and analysis. We've accepted that mathematics contains objects that defeat measurement, making the foundations of measurement theory rest on unmeasurable things. The Banach-Tarski paradox shows the axiom of choice leads to counterintuitive results. But rejecting it creates mathematics where vector spaces lack bases, infinite sets can't be compared, and bizarre cardinality results emerge. Accepting it means accepting that mathematical existence differs from physical possibility, and that fundamental mathematics rests on arbitrary conventional choices. We tried to eliminate a paradox about doubling spheres, and discovered that mathematics itself contains arbitrary conventional choices determining what's true, with no fact of the matter about which choice is correct. The Banach-Tarski problem is minor compared to the problem that mathematical truth is partially arbitrary. The EPR Paradox and Non-Locality. In 1935, Einstein, Podolsky, and Rosen proposed a thought experiment showing quantum mechanics is incomplete. Measure one of two entangled particles, and you instantly know the other's state, regardless of distance. Either information travels faster than light, violating relativity, or particles had definite states all along, violating quantum mechanics. They concluded quantum mechanics must be incomplete. Hidden variables determine states locally. This paradox challenged quantum mechanics for decades. In 1964, John Bell proved that any hidden variable theory must be non-local. If hidden variables exist, they must allow faster-than-light influences. In the 1970s-80s, experiments tested Bell's inequalities and confirmed quantum mechanics. Nature violates Bell's inequalities, meaning reality is fundamentally non-local. This resolves the EPR paradox. Quantum mechanics is correct and complete, and nature is simply non-local. Entangled particles are instantaneously correlated regardless of distance. Problem solved. But accepting non-locality creates paradoxes far worse than EPR. First, it violates relativity's fundamental principle that nothing travels faster than light. Relativity's speed limit isn't just about matter or energy. It's about causality and information. If entanglement allows instantaneous correlation, something is connecting distant particles faster than light. We resolved EPR by accepting that quantum mechanics violates relativity's most basic principle. Second, it creates the preferred reference frame problem. Relativity says simultaneity is relative. No absolute notion of at the same instant exists. But quantum entanglement requires simultaneous correlation. When particle A is measured, particle B's state instantly correlates, but instantly is meaningless in relativity. Whose reference frame determines what's simultaneous? Non-locality requires absolute simultaneity, contradicting relativity. Third, it raises the question, why can't non-locality transmit information? Quantum correlations are useless for communication because measurement outcomes are random. But why? If particles are instantaneously connected, why can't you use that connection to send messages? The standard answer is that you can only see the correlation after comparing measurements, which requires slower-than-light communication. But this seems arbitrary. Why does nature allow non-local correlation but prevent non-local communication? Fourth, it makes causality problematic. If measurements at A instantly affect B, does A cause B's state? But in relativity, different observers disagree on which event happened first. One observer sees A measured before B, another sees B before A. So, who caused what? Causality becomes observer-dependent, creating even worse problems than the original EPR paradox. Fifth, accepting non-locality means accepting action at a distance, which physics abandoned centuries ago. Newton's gravity acted instantaneously at a distance, which troubled Newton himself, and which relativity replaced with local field interactions. Quantum non-locality brings back action at a distance, contradicting physics' hard-won principle that all influences are local and field-mediated. Sixth, it creates the measurement problem in its most severe form. Entangled particles are correlated but individually random. The correlation only appears when comparing results. But how does particle B know what happened to particle A to correlate appropriately? There's no signal, no field, no mechanism. The correlation is a causal, effects without causes. Seventh, non-locality suggests space-time might not be fundamental. If particles are instantaneously connected, regardless of spatial separation, perhaps space isn't basic to reality. Some physicists propose space-time emerges from quantum entanglement patterns. We resolved EPR by accepting that space might be an illusion emergent from quantum information rather than fundamental. This is far more radical than hidden variables. Eighth, accepting quantum mechanics as complete and non-local means accepting that reality is fundamentally non-deterministic and contextual. Properties don't exist until measured. Measurement outcomes are random. And what's measured depends on measurement choice. We traded hidden variables, which would make reality deterministic and objective, for a reality that's probabilistic, observer-dependent, and context-dependent. The EPR paradox suggested quantum mechanics was incomplete. The resolution proved it's complete, but this requires accepting non-locality, violation of relativity, acausal correlations, return of action at a distance, possible emergence of spacetime from entanglement, and fundamental indeterminism. We resolved one paradox about completeness by accepting a reality more paradoxical than Einstein ever imagined. Schrödinger's cat and quantum measurement. In 1935, Erwin Schrödinger proposed a thought experiment to show how absurd quantum mechanics becomes at macroscopic scales. A cat is in a box with a device that has a 50% chance of releasing poison based on a quantum event, radioactive decay. Until observed, quantum mechanics says the atom exists in superposition, both decayed and not decayed. This means the cat is both alive and dead simultaneously, until someone opens the box and observes it. This is absurd. Cats are definitely either alive or dead, not both. Schrödinger meant this as a critique showing quantum mechanics can't be the complete description of reality. Something must determine whether the cat is alive or dead before observation. The standard resolution is the Copenhagen interpretation. Quantum superposition applies to microscopic systems, but measurement causes collapse to definite states. The cat is in superposition only at the quantum level. Macroscopic systems are always definite. When we open the box, we don't create the cat's state, we reveal it. But this resolution creates far worse problems than the original paradox. First, it requires defining measurement. What counts as observation that causes collapse? Does it require consciousness? A human observer? Any interaction with the environment? If any interaction causes collapse, then isolated quantum systems never exist. Everything is constantly collapsing through environmental interaction. But experiments show quantum behavior persists in increasingly large systems. Where exactly does collapse happen? Second, it creates the preferred basis problem. Quantum superpositions can be described in multiple incompatible bases: position, momentum, energy, etc. When collapse occurs, which basis does nature choose? Why does the cat collapse into a live dead, rather than some quantum superposition basis? There's no explanation for why certain properties become definite while others don't. Third, it makes consciousness potentially fundamental to physics. If collapse requires observation, and observation requires consciousness, then consciousness determines physical reality. This seems backwards. Consciousness should emerge from physics, not determine it. But avoiding this requires defining measurement without reference to consciousness, which no one has done successfully. Fourth, the collapse process itself is paradoxical. Schrödinger's equation describes smooth, deterministic evolution of the wave function. Collapse is instantaneous, random, and irreversible, completely different from normal quantum evolution. Physics contains two incompatible processes: smooth evolution and sudden collapse. Why? When exactly does one replace the other? Fifth, alternative resolutions create their own paradoxes. The many worlds interpretation says the cat is both alive and dead in different branches. No collapse occurs, the universe splits. But this requires accepting infinite parallel universes for every quantum event, as discussed with the grandfather paradox. We trade one absurdity, superposed cats, for infinite universes. Sixth, decoherence theory says interaction with environment makes superpositions effectively vanish without true collapse. But Decoherence doesn't solve the measurement problem. It just explains why we don't observe superpositions. The cat is still technically in superposition. We just can't detect it. This doesn't explain why our observation yields one definite outcome rather than experiencing the superposition. Seventh, if collapse is real, it appears to violate energy conservation. The wave function before collapse describes multiple possible outcomes with different energies. After collapse, one energy is definite. Where do the other potential energies go? Some interpretations say energy is conserved on average across many measurements, but this makes energy conservation statistical rather than absolute. Eighth, accepting that macroscopic systems can be in superposition, which experiments increasingly suggest, means Schrödinger was right. Quantum mechanics does lead to absurd macroscopic implications, but rejecting macroscopic superposition requires explaining where quantum behavior stops and classical behavior begins, which no one can do. Ninth, the cat paradox reveals that quantum mechanics treats measurement as special, different from other physical interactions. But measurement is physical interaction performed by measuring devices made of quantum particles. How can quantum systems measuring quantum systems cause something qualitatively different, collapse, from quantum interactions not considered measurements? Schrödinger's cat asked, how can cats be in superposition? The Copenhagen resolution says, measurement collapses superpositions, so cats are never actually superposed, but this requires defining measurement, unsolved, explaining preferred basis, unsolved, potentially making consciousness fundamental, absurd, accepting two incompatible physical processes, collapse versus evolution, and either accepting macroscopic superpositions, Schrödinger's absurdity, or explaining quantum classical boundary, unsolved. Alternative resolutions require infinite universes, many worlds, or accept that superpositions don't really vanish, decoherence. Every solution to the cat paradox creates measurement problems worse than the original paradox about cats. We resolved paradox about one cat by making the entire measurement process paradoxical, undefined, unexplained, and possibly requiring consciousness to determine physical reality. The Ship of Theseus and Mereological complexity. The Ship of Theseus is an ancient identity paradox. Theseus's ship has all its wooden planks gradually replaced. Eventually, no original planks remain. Is it still the same ship? Most say yes. Gradual replacement preserves identity. But now take all the removed original planks and reassemble them into a ship. Which ship is the real ship of Theseus? The solution philosophers typically offer. Identity over time isn't absolute, but conventional. We decide based on continuity, function, and our practical interests which ship counts as the same. There's no fact of the matter. Identity is stipulated by us for practical purposes. But this solution creates metaphysical problems vastly worse than the original paradox. First, it makes all identity conventional. If the ship's identity is our stipulation rather than objective fact, this applies to all objects. Tables, chairs, mountains, planets, none have objective identity over time. Whether something is the same object or a different object becomes a matter of linguistic convention, not metaphysical reality. Second, it creates problems for personal identity. Are you the same person you were 10 years ago? Your cells have been replaced, most of them. Your memories differ, your personality has changed. By Ship of Theseus logic, your identity is conventional stipulation. But if personal identity is conventional, moral responsibility becomes problematic. Should we punish someone for crimes committed by someone who is only conventionally the same person? Third, it challenges physical law. Conservation laws say the same particles persist over time. But if identity over time is conventional, what does it mean for a particle to be the same particle at different times? Physics seems to require objective identity, but the ship solution makes identity conventional. Fourth, it creates the problem of vague objects. If a ship gradually changes from all original planks to no original planks, there's no precise moment when it stops being the original ship. Objects become vague. No fact determines their boundaries or identity. But classical logic requires bivalence. propositions are either true or false. This is the original ship becomes neither determinately true nor false during transition, requiring revision of logic itself. Fifth, quantum mechanics makes this worse. Quantum particles are indistinguishable. Two electrons aren't just similar, they're identical in a stronger sense than classical objects. But if classical identity is conventional, what about quantum identity? Are quantum particles conventionally identical? Or does quantum mechanics reveal true metaphysical identity that classical objects lack? This splits reality into quantum objects with real identity and classical objects with conventional identity. Sixth, it creates composition problems. If identity is conventional, is composition conventional too? If we conventionally decide whether the ship with new planks is the same ship, do we also conventionally decide whether the planks compose a ship at all? This leads to Mereological nihilism, the view that composite objects don't really exist. Only fundamental particles arranged shipwise exist. But then, fundamental particles face the same problem. Seventh, it makes language deeply problematic. When we say the ship, we seem to refer to a definite thing. But if ship identity is conventional, what are we referring to? Not objective reality. That has no ships, only arrangements of matter we conventionally call ships. Reference becomes conventional too, making language unable to describe objective reality. Eighth, it connects to the problem of change. If the ship with new planks is conventionally the same ship, despite being physically different, then objects can remain identical while changing. But how? Change means becoming different, which seems incompatible with remaining the same. We've accepted that sameness through change is conventional stipulation, making the metaphysics of change rest on human linguistic conventions. The ship of Theseus asked, "Which ship is the original?" The solution says, neither ship is objectively the original. We stipulate identity conventionally. But accepting this makes all identity conventional, destroys the metaphysical basis for personal responsibility, challenges physical law, requires vague objects and new logic, splits quantum from classical reality, threatens composition, makes reference conventional, and leaves change metaphysically unexplained. We resolved a paradox about one ship by making all objects' identities paradoxical, conventional rather than objective, vague rather than determinate, stipulated rather than discovered. 10 paradoxes, 10 solutions, 10 larger paradoxes created by solving them. Russell's paradox resolved by axiom systems, creating Gödel's incompleteness, theorems showing mathematics can't prove its own consistency. The grandfather paradox resolved by many worlds, creating infinite universes and destroying personal identity. The liar paradox resolved by Tarski's hierarchy, making truth undefinable and requiring infinite metalanguages. Zeno's paradox is resolved by infinite series, accepting that space is infinitely divisible despite leading to the Banach-Tarski paradox. The Bootstrap paradox resolved by consistency constraints, requiring cosmic predetermination and causeless causes. Maxwell's demon resolved by connecting information to entropy, making information physical and creating the black hole information paradox. The Banach-Tarski paradox, forced by the axiom of choice, which can't be rejected without losing most of mathematics. The EPR paradox resolved by accepting non-locality, violating relativity, and requiring a causal correlations. Schrödinger's cat resolved by measurement collapse, creating the measurement problem and potentially making consciousness fundamental. The ship of Theseus resolved by making identity conventional, destroying objective metaphysics. Every solution makes things worse. We fix specific contradictions by accepting general principles that create broader contradictions. This pattern suggests paradoxes aren't mistakes in our reasoning that better logic will eliminate. Paradoxes might be fundamental features of reality, logic, and mathematics. Every resolution reveals deeper paradoxes because paradox goes all the way down. Gödel proved mathematics must be incomplete. Tarski proved truth must be relative. Bell proved reality must be non-local. Banach-Tarski proved the axiom of choice creates impossible decompositions. These aren't failures, they're fundamental limits on coherent systems. Perhaps reality itself is paradoxical. Not contradictory in ways that make it incoherent, but structured such that perfect logical consistency is impossible. Every attempt to create complete, consistent, paradox-free systems fails because completeness, consistency, and freedom from paradox are mutually incompatible. We have three options: accept incomplete systems with unprovable truths, accept inconsistent systems with contradictions, or accept systems free from paradox that can't describe everything important. We can't have all three. The resolutions we've examined choose incompleteness. Mathematics is incomplete. Gödel. Truth is incomplete. Tarski. Identity is indeterminate. Ship of Theseus. Causality is non-local and acausal. EPR. Each resolution trades explicit paradox for fundamental incompleteness. But incompleteness is itself paradoxical. Systems that can't prove their own consistency, truths that require infinite hierarchies, identities that are conventional. These aren't clean solutions. They're admissions that reality exceeds our ability to describe it coherently. Maybe that's the final paradox. Resolving paradoxes is impossible. Every solution either hides the paradox at a deeper level or transforms it into a different paradox. The goal of paradox-free understanding might be incoherent. We can choose which paradoxes to accept: Russell's set or Gödel's incompleteness, one grandfather or infinite universes, liar sentences or infinite meta-languages. The paradoxes are unavoidable. We only choose their form. 10 paradoxes that create larger paradoxes when resolved. The pattern suggests that paradox isn't a problem to be solved, but a condition to be accepted. Reality, logic, mathematics, and metaphysics might be fundamentally paradoxical, not broken, but structured in ways that prevent perfect coherence. The attempt to resolve paradoxes reveals the final paradox. We can't eliminate paradox without creating something more paradoxical. The solutions are worse than the problems, and that might be the deepest truth we can know about the structure of reality.